Welcome back to ME 760 Engineering Analysis 1. So last time I want to remind you it was what we discussed last time. So last time we just discussed the integration on surfaces, or the double integration from the point of view of integrating a scalar function. So this was just a review for the Calc 2 courses that you took already in the university here. And it's nothing to do with the vector functions. So today's lecture will be discussing the first of the two methods that I discussed at the beginning of the chapter. One of them is how to transform a double integral into a line integral, and the other one is how to transform a volume integral to, or triple integral to, a double integral to surface integral. So today we will discuss the first of those two methods, and this is Green's theorem. And this is sometimes they name it Green's theorem in a plane. So this will use it to transform a double integral to line integral. So let's assume that in the xy plane, for example, I have a contour like this. So this is A, B, and let's assume the minimum in this part of the contour. Let's call it T. This point, let's call it S, and this point, let's call it U. So this is just the contour C, and the part of the contour, the lower part is STU, and the upper part, let's call this C, and this is D. So let's call T here, and this is V. So this part of the contour is TSV. And this contour, closed contour, contains a region R. So we'll assume that C just B closed curve in the XY plane, and R is simply connected. So what do we mean by simply connected? Last time we defined the simply connected as what? Any closed curve inside this region. Once you shrink it, it will come to what? So a point. Then we said if you have something like this, this is simply connected. If you have something like this, and you have something, for example, like this, or something like this, this is doubly connected. So we said if you have n-1 holes inside the curve, it will be n connected, n-fold connected. So this is n-1 is what? It's only, so let's say n-1 equal to 1. So n is equal to what? So this is doubly connected, okay? And why it is doubly connected? Because the area, the region here, is connected from here and is connected from here. So twice. It's doubly connected. Did you understand, guys? So now, this is simply connected region like this. So we can write the Green's theorem as the double integration over R for certain function Q d by dx for Q minus dp by dy integrated over the area dx dy will just be equal to the closed contour, the integration over the closed contour of the function p dx plus q dy. Another form of Green's function is integration over R of curl of an excuse me of a function f integrated over an area. So the area is located in the xy plane, and the unit vector for the area is perpendicular to the area, so it will be in the z plane. This will be equal to the closed integration over the contour C of f dr, and the function f here is nothing more than a function of x and y, p in the direction of I plus q in the direction of j plus 0 in the direction of k. So, excuse me, how we prove it? So here is the proof. So the beauty of this theorem is you can transform a double integral for a specific functions, let's say q and p in this case, to a line integral for the same functions. But now you use the derivatives of those functions here, and here you use the function p and the q. And I will show you a couple of examples in a minute. So let's assume that if we will integrate over x, we will be integrating from what? A to b, okay? And when we will integrate over y, we'll be integrating from c to d. So if we will be integrating over x from a to b, y will go from this curve, which is what? st u, and y in this case will be y of y1 of x, and y2 here will go on the y2. It will be a function of x, but will be on the other part of the contour, which is svu. So the first thing is to assume that y is equal to y1 of x for the curve. What curve we said? STU. And it will be what? Y equal to y2 of x for what part? S what? SVU. Then we will look at the first first dp by dx. So the integration of over the contour of dp by dx, dq, sorry, by the db by dy, sorry, I'm sorry, db by dy, which is the second part here. So this is db by dy over dx dy. I can write it as what? Can write it as you will go from a to b for dx, and then you will integrate db by dy over dy. So dy will go from lower y, which is what? y1 of x, to upper y, which is what? Of x. So this will give you what? This will give you the integration from a to b dx, and what's the integration of db by dy? So it is just what? P of what? X and y2 of x minus P of what? X and y1 of x. Yes, guys? This is integrated over what? Delta x now, from a to b. So I can make this as what? As the integration from a to b for the first part, which is p of x and y2 of x dx, minus the integration from a to b, b of x and y1 of x dx. Okay, I will leave this as is. Then I will flip the sign here. I multiply by negative, and if I multiply by negative, I do what? Yes, guys? So, what's this? You integrate from a to b for a function p of x, yes, x and y1, yes, so integrate from a to b over y1, then you go from b to a over y2. So what's this? This is the integration of what? b dx over the closed contour. Yes, guys? Because now I go from one part of the curve over y1 and I return over y2. So this is the closed integration of b over b dx, and there is a negative sign. Yes? I can still do the same. So let me leave the curve. So let's do the same for x now. So let's assume that x is x1 of y for the contour to TSV. Now we will integrate in what direction? We'll integrate over what? Over y. Okay, we'll integrate first over x, then we will move the integration over y. So on the curve TSV, x will be what? x1 of y, and on the other part it will be x2. What's the other part? So this is TSV, and the other part is what? TUV. So we'll do the same, but now for double integration over R for dq by dx. So this is dx dy. So we can separate this to two integrals. The first one, I will integrate the dq by dx over what? Delta x, and I will integrate dy. dy will give me from c to what? D, and dx will be from what? x1 of y to x2 of what? Of y. Now, we'll do exactly the same. So this will give us from c to d dy, and what's this integration? Just what? Q of x2 of what? Of y, and y minus q of x1 of y and what? Y. Okay, guys? So now we can do exactly the same. So this will be from C to D, Q of x2 of y, and y integrated over delta y, minus C to D, Q of x1 of y, and y delta y. So I will leave this one the same, and then I will flip the sign here. So I have to flip the order of the limits. Okay, guys? So if I change this to plus, this should be go from where to where? D to what? To C. So now you go from D to C, point D to C over x1, and then you go from C to D over x2. So this will give you what? So this will give you the closed integration of q d what? Q dy for this one. So we'll call this 1, and we will call this 2. So if you subtract 1 from 2, if you subtract 1 from 2, you will get the following result. What's 2 now? It's here. It's q dq by dx over r dx dy, but I will put dx dy here, and I will subtract from this one the other one. So what's the other one? dp by dy. So dp by dy dx dy, and this will be equal to the contour integration. So this will give me q dy and minus p dx. I will multiply by minus sign again, so this will change to what? To plus p dx. So this is the proof of this one. If you want to memorize it, so that, let's say in the exam or you are doing any work, if you want to memorize it, just flip the order I will show to you. You will put the double integration sign with r, then you will get any function. Let's say q. So the first function you will differentiate it with what? With x. Okay? But the same function without differentiation, q, but multiplied by the opposite, so it will be y. So d by dx, same function multiplied by dy, and then minus sign here. The other function is p, so db by dy, it will be p multiplied by x, but plus sign. Easy way to memorize. Yes. Do you have any question, Namal? Okay. So did you understand it? Do you have any question? So this is a very nice theory to transform double integrals to line integrals. And of course, the two functions, p and q, they are assumed to exist. The derivative of those two functions assumed to exist. So dq by dx and the p by dy exists. And this one also, this derivation also will holds for the multiplying or multi-connected regions. Where in multi-connected region, where you have, let's say this is an R inside a contour, and this contour here, C, there is another contour, C2 inside, and the region R is the region in between the two contours. So this will also hold, the Green theorem will also hold in multiply connected or multi-connected or multiply connected region, where in this case C is along all boundaries for the region. So C1 and C2 is along all the boundaries for the region that you are integrating over. And the most important thing is you must, when you do the closed integration, you must transverse the boundary in positive sense, and I will tell you what do we mean by positive sense. Means that R is to the left of the curve all times. Here's the curve C is C1 plus C2. What does it mean? Okay, if you are doing the integration over the curve C1, so while you are moving in this direction over C1, always the region R is to your left. Okay guys, so region R is not to my right, it's to my left. Go here, where is region R? Your left. Here is your left, here is your left. Okay, then when you go here, you have to go in the opposite direction so that the region R is to your left. Do you understand? So when you go here, region R is to my left, region R is to my left, region R is to my left. So I have to go the opposite direction inside. So outside I go in this direction, inside I go in this direction. So this is the positive sense. So when you do this green transformation and you integrate over the contour, you have to do this while you are doing the integration. Did you understand? So if I bring a homework problem, for example, and you want to integrate over a contour, you knew what is the positive sense. Otherwise, you will get an error. You will get a negative sign or something like this in the integration. Did you understand? Okay. So now let's take a couple of couple of applications for this beautiful theory here. So one application is to find the area as integration over a closed contour. So instead of just integrating over a double integration, just we will integrate over a contour now. We will transform the area to a contour integration. So what's the area? In double integration R, the area is what? dx dy in Cartesian coordinates. And Q and P is any functions. For example, I can pick as long as Q and P, they have derivatives. The derivatives do exist. So let's pick, for example, B equal to 0 and Q equal to X. So what's dP by dy is what? 0. And what's dQ by dx? Is equal to 1. Now, let's now see what's going on here. So can you substitute now in this equation? So this will give you what? What's dq by dx? 1. Okay, and what's dB by dy? 0. So this is 1 multiplied by what? Dx by dy, which is just what? The area. And what's P? Guys, what's P? 0. And what's Q? X. X dy. Okay, guys? So I will call this 1. So this is, you now change the area from a double integration dx over dx dy to just a closed integration of x dy. Let's assume that I can pick P to be negative y and Q to be 0. So again, what's dP by dy? Negative what? 1, and dq by dx is what? 0. So what this will be again? Area equal to over R. dq by dx is what? 0. And dB by dy is negative 1 multiplied by negative 1 is what? 1. So this will leave you with the definition of area dq by dx. And it is equal to, what's P? Y dx. And what's Q? 0. So I will call this number 2. And then I can just add those two equations, 1 and 2. So when I add those two equations, what I will get? If you add 1 and 2, you will get what? 2a is equal to what? X dy plus y dx over closed contour, or the area simply will be half of this. I will call this number 3. Okay, guys?
Where did your negative go?
What negative?
For P.
For what?
P was negative y, but then on
This one?
no, in your bottom.
Oh, this one?
Yeah. Then
Oh, here, you mean here?
Mhm.
Yeah, you are right. I'm sorry. So this will be negative. I'm sorry. This will be negative. Okay, so let's see an application of this. We have ellipse like this. And this is A, this is P. And this is the x coordinate, this is the y coordinate, and this is the contour C. So what's the equation of ellipse? X square over a square plus y square over b square is equal to 1. This is the equation for ellipse, as all of you know. In parametric form, instead of just, if you try to integrate the area, what you will do? So you will pick, yes, you will pick dx, then you will integrate it over dy, or you will pick what? You will pick dy and then you integrate it over what? Dx. This is dy and you will integrate it over dx, and this is d what? Dx and you integrate it over delta y. And you have to know what's the equation here, what's the equation here, so you'll know what's the limits for integration, yes? So parametric form will be a little bit easier. So in parametric form, x is equal to what? A cosine u, and y is just a sine u, where for both of them, u is greater than 0 and less than 2 pi. So now I can calculate the area. So what's the area? I can calculate the area from the above equation here. Area is just equal to 1/2 the integration of what? Over the closed contour? See, x dy minus y dx. This is equal to 1/2 integration over the closed contour of what's x dy. I can make this as x dy by du minus y dx by du, then make it like this. Did I make any difference? Does it make any difference? No. Okay. So what's this integration? 1/2 here. So what's x? A cosine u. And what's du by the du by dy? Dy by du? A cosine what? Minus what's y? A sine u. Dx by du, negative a cosine u. So negative by negative is positive, and this will give me what? A what? A sine u du. What's this? A square sine square u a square cosine square u. This will give you what? This will give you a square du. A is constant. A is what? Is constant and will be outside, so this will give you 1/2 oh, there is the other one is b, so sorry guys. Y is p sine u. I made a mistake. Okay guys, so this will be what? P b. So this will be
it's a cosine u times b cosine.
And a there is ab. So let's make it like this. AB, and the other one is AB sine square. So this will be AB du. Okay guys? So this will give us 1/2 AB, the integration over u, and u will go from 0 to what? To pi. So this will give you what? AB by, and this is the area of the ellipse here. As alternative way to do it, instead of using this formula, which is a combination of equation number 1 and equation number 2, we subtract them from each other, we got this formula. We can use only one formula, and the only one formula is what? Is area equal to x dy over the contour, as you remember. Yes guys? So instead of 1/2, we'll use this one only. Yes? Because the area was equal to the contour integration over this, and area was equal to the contour integration over this, and we add them together, give us 2 area equal to this integration, so we divide by 2. So let's assume that we will use only one of those formulas to see if we will get the same results or not. So what's x now? I can write it as x dy by du. So again, what's x? A cosine u, and du by dx is what? B? No, b cosine u du. So this will give you what? AB, the integration of cosine square u du from 0 to 2 pi. What's cosine? What's cosine square u? or cosine square x or whatever. It's 1/2 plus 1/2 cosine 2u. If you return back to your definition for trigonometry, you will find that this is the value for cosine square u. So this will give me what? AB, and I will integrate over 0 to 2 pi half du plus 0 to 2 pi cosine what? 2u du. What's this integration? When you integrate a cosine function over a full period. This is a cosine function over a full period, or a sine function. So this is, one second, let's assume that this is the sine. This is the sine over full periods, and the cosine will be, go like this, like this, like this. So what's the integration over a full period? So for the cosine, this is positive and this is positive. Those two will combine together, will give you what? A half period, yes? And this is what? A half period. So when you add positive and negative, you will get what? 0. So like sine. Sine, this is the upper half, this is the lower half, they are identical, it will give you 0. So whenever you will integrate a function over one full period, if it is periodic, it will give you what? 0. If it has positive equal to the negative in half the period, this will give you 0. So this is 0, and this is what? Half multiplied by 2 pi is what? Pi, so this will give you what? AB pi. So it gives the same results, guys?
Excuse me?
Yes.
Can it be applied to all the functions, or
Can what?
Can it be applied to all the areas, or just because it is symmetric?
If your function is symmetric, like the cosine and sine, and if you integrate over the full period, if the function first of all is periodic, and it has let's say a period of 2 pi like this, something, I will show you another example. If you have something like this, and those two areas are exactly the same, and this is from 0 to 1. So if you integrate this function from 0 to 1, it will give you 0, because you are adding this area, and those are two identical areas.
Yeah.
If you have something like this, it will give you 0. But if you have something like, this will not give you 0.
What I asked is about that equation, that A equals the integral.
This one?
Yeah.
No, it will give you the same result. It does not matter whether you are symmetric or not.
Okay.
Okay? And this is what you see here. Okay, guys? It depends on the choice of P and Q, of course.
Okay.
What value of P and what value of Q, or what function of P and Q you choose.
Are there any constraints for?
What do you say?
Are there any constraints for choosing P and Q if we want to use that equation?
I have to think about it, about the constraints. Again, P and Q, they should be continuous function, and their dP by dQ by dx and dP by dy should exist. Those are the two conditions that we just discussed.
Yeah, I think that are the constraints for the previous equation.
It is the same for this one also.
The same?
Yeah, because we derive this area from the Green's equation. How did we derive it?
Well, you assume that
R,
U is 0.
and this is dQ by dx minus dB by dy over dx dy equal to P dy or B dx plus Q dy. Yes, guys?
Yeah.
So we assume a function P and a function Q, but when you assume or propose a function, it should fulfill the Green's theorem. So it should fulfill that P and Q are continuous and their derivative exists. Okay, guys? If you do not understand, let's postpone it to the, because I need to finish the lecture. Then I can talk to you about it later. Okay? So now, what's the second application that then we can look at is the transformation of the nabla square to line integral. So if you have nabla square and you want to simplify it to line integral, Green theorem will give you a very good solution for this. So we will consider a function omega of x and y, and this omega of x and y is continuous and with continuous derivatives and with continuous first and second derivatives in a region R, in R. And R will be, we have R region like this, and this contour here is C, and let's assume that this is delta S is part of the contour, and then this is an R prime, which is just the tangent to the curve, and the normal to the tangent is just in hat. So we will set our functions P to be d omega by dy and Q to be t omega by dx. Then what's dq by dx? dq by dx is what? d square omega by dx square. And what's dp by dy? Negative d square omega by what? By dy squared. Then we will apply the same Green's theorem again, dq by dx minus db by dy over region R dx dy equal to q dy plus p dx over in the contour C. So what's this term? The first term, what's dq by dx? d2 omega by d what? By dx square minus dp by dy d squared omega. So this will be plus d square omega dy squared. So this is what? This is what? Yeah. Over R. What's this? Remember what we want to transform. Transforming of what?
Nabla squared.
So this is what?
Nabla squared.
Nabla square of what?
Omega.
Of omega. So this is nabla square of omega dx dy. So let's look for the second part here. What's the second part? Right hand side. Is what? B dx plus what?
Q dy.
Q dy is equal to, what's P?
Negative dw or d omega.
Negative d omega by dy. This is dx. Yes? Plus, what's Q?
D omega.
D omega by dx dy. And I can write it again as the following. If I divide here by ds, which is the unit length on the contour or on the curve C, and I divide here by ds again, then I have to put ds here. I did not do anything by introducing this. So now I can make this as d omega by dx in the I direction plus 2 omega by dy in the jth direction dotted with dy by ds in the I direction plus minus, dx by ds direction in the j ds. What's this?
Lambda omega.
Hmm?
Nabla omega.
Nabla omega. So this is the gradient of omega. Dotted with, what's this? It's a little bit strange, but we will prove it in a second. This is the n, the unit normal to the curve at here. So anywhere in the curve, if you want to get the unit normal for a curve, just it will be dy by ds, where s is what? Is the length of the curve, okay? And dx by ds. We will prove it right now. We will prove it right now. So again, I told you several times that nabla omega dot n, this will give you what? From last chapter, we said that if you take the dot product of grad of a function, you take the dot product. To remind you, when I said gradient of f dot s, do you remember this? Or let's say the gradient of f dot, let's say dot dot s. Let's say unit normal is called s. I told you last chapter is this is df by what? It will be the rate of a change of the function f in the direction of what? In the direction of s. So this is again gradient of omega dot n. So this will be what?
D omega.
D omega d what? dn. So now I can rewrite my transformation as following. So the nabla square omega over an area dx dy in a region. So all what you will do, you have a region R and you have some function omega inside this region R defined in this region R, and by taking the nabla square and you want to integrate over the surface area, is simply equal to what? Is d omega by dn. It's just you transformed a double integral for nabla square inside a region R to just integration over a contour, and you will get the rate of a change of the same function omega but on the boundary. Yes, with respect to what? N. So it is now a boundary integration, and this is very, very useful. Now let's show to you as a side why this is equal to n. So let's assume that you have a function r of s, which is this one. Let's assume that this is r here. Each one of those points, it has a point on the curve. It has a position vector r, and this position vector r would be a function of s. Okay, so this is r of s. So if you differentiate this, r prime of s will be what? Dr by ds, and this is equal to, R has two components, x and y, yes? So this will be what? dx by ds, in what direction? I plus dy by d what? By ds in the jth direction. Okay guys, so if I just dot n, which is the unit normal here, where is the r prime? We assume that this is r, this is n. Yes, we assume that this is the unit vector n. So let's put it here. dy by what? By ds in the I, minus dx by ds in the j, dotted with, this is r prime. So what's r prime? dx by what? By ds in the I, plus dy by ds in the j. If this indeed a unit normal, if I dot it with the vector r, it should give me what? If they are normal, they should give me what? 0. Now, do this. So the first one will give you what? dy dx, yes? By d what? By ds squared. Or it will not be like this. It will be just, because you cannot write it like this. It is dy by ds, dx by ds. Yes? And the other one, it will give you what? dx by ds, dy by what? By ds. And this gives you what? So is it the normal or not normal? Normal. So that's it. I will stop here and continue next time. So next time we will take some applications, and then we will move to how to transform a triple integral to a double integral, and we will conclude with the chapter. Did you have any question? Excuse me. Did you have any question so far? Okay, guys. Have a good day.